We often talk about OR gates and AND gates, and we have this table related to the logic gates, that how it is constructed. For example, we say when one state is on, another is off, then for OR gate it becomes on, but for AND gate it is off. But we rarely talk about the circuit behind these logic gates. In the previous video, we solved a circuit for OR gate, but in this video, we will talk about this circuit and see if this belongs to the AND gate logic. So we have to prove that the network presented in this figure is for AND logic. And by AND logic, we know that if one input is on and another input must be on. Okay, so we will have an on state over here. Otherwise, we will have off states. This is the basic concept behind AND logic gate. So let's see if we can prove that in this numerical problem. So we have a circuit over here which has two diodes, one resistor, one additional built-in battery source in the circuit, and we have two input terminals where we will provide the input to the circuit. In the previous example, the diodes were in forward bias condition. They were in this direction. Okay, if you recall that for OR gate logic. And in this video, they are in reverse bias condition. And another difference is that we have an additional source after the resistor. Between ground and resistor, we have a source voltage of 5 volts. So now, once again, we will do it step by step. We will analyze 4 cases. First, we will give an input to first input, then second input, then input to both terminals, and at the end, no input to the terminals to see how we can construct this table. So in the first case, we have an input at the first terminal and no input at the second terminal. So what happens is that we will have to see if this diode acts as an open circuit or closed circuit. It will act as an open circuit if this will be in reverse bias condition. We can already see this, that this is in reverse bias condition, but let's sketch it down over here. So we have this diode in this direction, okay? This is the first terminal connected with the battery source, okay? And then we have this second diode, which is grounded, okay? And then we have this common node between them, resistor, battery source. Let's put this like this, and we have a ground. So E is equal to 5 volts, 1 kilo ohm resistor, D2 and D1. We have this positive terminal, negative terminal, input is 5 volts. Now, this is negative terminal of the diode. This is positive terminal of diode. We know this. When a diode is made like this is the symbol of diode. So this terminal is always positive, this is negative. So in that case, this diode is in the reverse bias because we can see positive terminal is connected with the negative terminal of diode. So this diode will act as an open circuit, right? So this will act as an open circuit. So this will be an open circuit over here. And this input voltage will have no influence in the circuit. So we will only have this component D2 in the circuit. So now what happens is that this is the positive terminal of this source, right? Indirectly, this positive source is connected with the positive terminal of diode. We can see that clearly over here. And this is the negative terminal, right? So what happens is that this diode will become in forward bias condition, right? For the case 1, when we have input voltage over here of 5 volts and 0 volts input, or you can say it is grounded. In that situation, the second diode will be like a forward bias conditioned, or you can say it will be short circuit. So in that case, what will happen is that we will have a voltage across this terminal and this terminal. Remember that the voltage is measured at this terminal, and then the second terminal should be towards the ground. So we have a battery over here. So unlike the OR gate logic, we will be calculating the output voltage between this node and the ground appears over here. Okay. So we know that when a diode is in forward bias condition, the voltage drop across it is 0.7 volt. So in this case, we drop against this second diode, which is 0.7 volts. That is also equal to V naught. We can see that, right? So this will be 0.7 volts, or you can approximate it to 0 volts. Now let's go and see the second logic or second case where we will have an input at the second terminal over here and no input at this terminal. We are doing the second case. Actually, this case is same as the previous one, which we have already done. So just to show you the figure over here, when we applied 5-volt input over here, and this was grounded, we saw that this is in open bias. This is not in open bias, sorry, this is open circuit. And this is open circuit because diode was on reverse bias condition. And then we solved this problem and we saw that the voltage drop across D2 is 0.7 volts, right? And that is also the voltage across this component, and we can calculate our output voltage of 0.7 at this node. Now let's go to the second case. In second case, we have an input at the second terminal instead of the first terminal. It is the same problem, but now we have an input at the second terminal. So let me draw this diagram over here. Let me draw it over here. So we have this V1 diode is connected over here, right? D1, V2 diode is connected over here, V2. Then we have this resistor, and this goes to this battery source and then grounded. Okay, this was 5-volt plus minus. Now, when the input voltage at the first terminal is 0 volt, so this means that this terminal is grounded. And when input voltage at second terminal, which is for the second case 5 volts, so this is 5 volts. Now we can see over here we have positive terminal, this is negative terminal. For diode, this is negative terminal and this is positive terminal. So we can clearly see positive terminal is connected with the negative terminal of diode. So remember that whenever opposite terminals are connected with each other, for example, for this case, we have this diode connected with the battery source, but the terminals are opposite with each other. So this is a reverse bias condition. Okay, so if this will be reverse bias condition, then what happens is that at this point we will have an open circuit, right? Exactly like this. So this will be this is 1 kilo ohm, this is 5 volts. So for D2 we have open circuit. Now what happens with the first diode is that we can see due to this positive terminal, which is the internal battery source, this positive terminal becomes connected with this positive terminal. So we get the diode to be in the forward bias condition because same terminals are connected with each other. So due to that, this diode will actually act as a 0.7 volt source because that is what is the value of diode when a voltage is dropped across a diode. We know this, that the voltage is always 0.7 volts if it is made using silicon material, right? So now the output at this point, which is V naught, this will become the output measured using this terminal and this terminal, right? So if we look at this table, this figure, it will be between this terminal and this grounded terminal, so which is 0.7 volts. So for the second case, once again, the voltage drop across this diode will be actually output, which is 0.7 volts. So we can assume it as 0 volts. So we can see over here, this is equal to 0.7 volts for the second case. Now in the third case, we will apply the voltage at both terminals and see what happens. Now this is the third case in which we apply the input voltage not 0.7 but 5 volts at both terminals. So when a voltage is applied over here, so let's draw this diagram to make it clear. Over here we have diode number 2, resistor, then battery source, and then a ground. E is equal to 5 volts, 1 kilo ohm resistor, D2, D1. They are connected to a battery 5 volts, right? Now we know that this is the negative terminal of diode, right? This is also the negative terminal of second diode. So when positive terminals are connected with the negative terminal, the diodes will be in reverse bias condition, and in reverse bias condition, it will act as a open circuit. We can see over here, open circuit. Okay, so this will be open circuit. So what happens in that situation is that this 5 volts will actually start appearing over here, right? So what happens in case 3 is that when we applied the input voltage at both terminals, we got this output of 5 volts. Is it clear? It should be clear. It's obvious that this 5 volts will start appearing over here, and there will be like open circuit for these two diodes. So now the next is the fourth condition, in which we will apply no voltage to the input terminals and see what happens in that situation. Now this is the fourth condition, in which no inputs are applied at the terminal. You can see over here 0 volts, 0 volts. So they are kind of grounded at this point. Now we will talk about if these diodes are in forward bias or reverse bias condition. Since there is no input applied at these terminals, so we will talk about the forward bias and reverse bias condition using this source over here. So this positive terminal is actually connected with the positive terminal of this diode, right? There will be some power dissipated and voltage drop across this resistor. That's not a problem. But due to this positive terminal and these positive terminals, these diodes will be in forward bias condition. If they are in forward bias condition, we know that the voltage drop across diodes is 0.7 volts. Across second diode, it will once again be 0.7 volts. So coming to this point, now we have to calculate the voltage at this point, right? So this will be a common ground between them. And since these two diodes, they are in parallel with each other, let me draw it over here as a battery source. So we have this grounded over here, and then we have this second diode. They are connected. So we are calculating V naught at this node, right? This is 0.7 volts. This is 0.7 volts. They are parallel with each other, so the voltage drop across them is equal. And that is also obvious using the voltage drop across diode, which is 0.7 volts. So now the voltage between this terminal and the ground, this will also be 0.7 volts, right? Because this part of the circuit, this is parallel. So the total voltage drop will be considered as 0.7 volts. So the output voltage will become 0.7 volts, and we can see it over here. Now we have completed this table, and we will compare it with the AND logic gate table and see if this circuit satisfies the conditions of AND gate logic table. On the left hand side, you can see a table. This table is for AND gate. We know that for AND gate, both states should be on, and then the results will be on state. Otherwise, they will be 0. So this is for AND gate. And now the table which we draw for this circuit, it has these results. When input was applied at the first terminal, we got an output of 0.7 volt, which is also like approximated as 0 volts for logic gates. This is also 0.7 volts, which was for the second case, and we approximated to 0 volts. The only working condition we got was that when input was applied at both terminals, we got a output voltage of 5 volts. This was the only operational circuit condition. And in the last case, no input was applied, and we saw once again it was 0.7 volts, and we call it as 0 volts, or we approximate it as 0 volts. So we can clearly see this is the third condition, right? Third condition, when both states are on, we get an output. For this circuit, when input was applied at both circuits, we got an output. Otherwise, all other states resulted in 0 volts or very low voltage. So we can say that this circuit actually represents AND logic gate. So it is proved.